MDM4U 3.0 Statistics of Two Variables. What we're going to be learning about in this chapter is how to describe correlations between two variables. And in order to do that, we can use regression models, which are functions that we may have seen in the past that can be used to describe that relationship as a trend or pattern occurs between two variables. So let's review each of the different topics that we've covered. In grade 9, we covered linear relations, and there are three different forms. We're going to start by talking about y is equal to mx plus b, which is slope y-intercept form, because m, which represents the slope of the line, in the form rise over run. And in point slope form, if we have two instances of a pattern on this line, we can say that the first point is x1, y1, and the second point is x2, y2. Subscripts in mathematics typically name the variable. So this formula can tell you the slope between those 2 points, and b is the y-intercept. Standard form is helpful just to see that when we bring all of the terms in the expression or in the equation over to the left-hand side, we have x in 1, our degree 1, and we have a scalar quantity c. X and y-intercept form. This is helpful for when you want to graph by using both the x and the y-intercept. You can find the y-intercept by letting x equal 0, substituting into the equation and solving for the remaining variable. And if you want the x-intercept, let y equal 0 and solve for the remaining variable. Next, in grade 10 we discussed quadratic relations, and they had different forms. Let's start off with standard form. In standard form, we can see that this is a degree 2 polynomial, meaning that the highest exponent on the polynomial expression is 2. So that is a characteristic of a quadratic equation. And even if it is in the form factored form, if you were to multiply these two binomials together, the product would have an x squared term, similarly for the vertex form. Each yields its own information. When you let x equal 0, you can quickly get the y-intercept c in standard form. Factored form lets us determine those x-intercepts, which can be critical points in many application problems. Similarly, the vertex form has its advantages. It tells you the vertex hk in this form of the equation, which is either a max or a minimum, the vertex of the parabola. Exponential equations are of the form y is equal to ab to the power x, where a is the initial value, the starting point, or y-intercept. B is the factor of growth, so whether you have exponential growth when b is greater than 1, think repeated multiplication by a number greater than 1 will make that value increase. And exponential decay, whenever we have a value between 0 and 1, we get a product that would be smaller than the original value. And that's why we see gradually decreasing, and it has a horizontal asymptote, meaning it approaches but doesn't cross a specific value. So graphically, we're going to talk about each of these types of relations. Linear relations are a straight line. Quadratic relations are a U-shape that we refer to as a parabola. So it's bell-shaped and symmetrical, or U-shaped. Exponential relations have that horizontal asymptote that we discussed, and it begins to grow rapidly or decrease rapidly. Lastly, in a table of values, we're going to discuss what characteristics can be used to identify linear relations, quadratic relations, and exponential relations. So we'll first look at our first differences for linear relationships. So here's a table of values, and we want to know what type of relationship exists between the two variables. The first differences are accomplished by taking the difference between adjacent values of y. If we have a consistent interval for our x values and the differences for our y values are the same, then that would mean that we've traveled horizontally and vertically the same number of units and then ended up back on the line. So this is a linear relationship because the first differences are equal. Next, if we take the differences of the first differences, we end up with our second differences, which is a test that can be used to determine whether or not a relationship is quadratic. So it's the adjacent first differences that we take in order to determine our Second difference is, if they're all consistent, then it's a quadratic relationship, as we see in this case. Lastly, we said that the exponential relation is based on repeated multiplication. So we can do a test for a table of values by dividing adjacent values in our table. So the x intervals are consistent. Dividing each of the y values that are adjacent, we end up with a consistent factor of 2. And this would be the base value b in our y is equal to a times b to the power x equation for an exponential relation. So the relationship is exponential because the ratios are equal.